Hello everyone, welcome to Industrial Application Station. I'm Rachel Wu. I'm a research associate in Fraunhofer IPA in Stuttgart. I will be the host of this section. This session will take around 75 minutes. We will have 3 speakers who will present their products, which is based on the ROS. And each presentation will take 20 minutes. And as you can see, we have the live discussion. If you have any question, you can post under the questions. And we also have some question in the polls. You can answer it there. And after all the presentation, we will have 15 minutes to answer the questions. Okay, so let me introduce the first speaker, Timo Steinhagen. He worked as a localization expert in a corporate internal startup at Bosch. He did his master's degree in mechanics at the Hamburg Technical University and the University of the Waterloo in Canada, and worked at the Waterloo Autonomous Vehicle Laboratory for 1 year, and then moved to Bosch corporate research, and then to the startup. So in his presentation, he will talk about developing software components for mobile industrial robotics based on ROS. Timo, microphone is yours.
Right, welcome again. My name is Timo Steinhagen. I'm here today from the Bosch group talking about software components for mobile robots. And this is the agenda I'm going to go through today. So I'm going to start introducing Bosch and myself for a little bit. Then I will talk about the role of Bosch Rexroth and the home of robotics in particular. Cover the topic of what we understand in software component, kind of a little about tooling and product development. And then I'm going to introduce you one specific component, which we call the locator, to you guys, and give a quick little outlook on the future. Quite a lot of stuff for 20 minutes. So I'm just going to touch on these topics, and I guess if there's any questions coming up, save them for later for a question and answer session, and we can discuss them in more detail. Yes, so Bosch, I guess you've all heard that name before. The Bosch Group is pretty big. We do 78 billion euros in sales every year. These numbers are from 2017, so they might have changed slightly, but not severely. I'm coming from Hamburg personally, and actually I have to admit that I knew Bosch as a manufacturer of power tools and laundry machines before I started working here. But as you can see, with 60% of our revenue, more than half of what we make is in the automotive industry. But that's just 60%. There's 40% of those 78 billion that we do not do in the automotive market. And the industrial technology is a very big portion of those. And this is where the robotics is also integrated. Yeah, so we have a little more than 400,000 employees worldwide. I'm one of those. As Royal said in the introduction, I started out at Bosch in the corporate research department doing software development for autonomous driving. And then a little later on, I moved to a corporate internal startup where we focus on doing software components for mobile robotics. That's what I'm going to talk about today. This is a corporate internal startup because of a kind of a development design within Bosch. So new topics that do not have like a classical development department yet, like automotive parts, for example, they either found a new one, or like we did, we started out as a startup to be a little decoupled from the standard Bosch development processes. And we are doing those now, but we didn't have to when we started out. Okay, so that's kind of Bosch and myself. And then there is still Bosch Rexroth, which is like a daughter company of Bosch, and the home of robotics. So Bosch Rexroth is a company doing industrial projects within Bosch. So they do lots of stuff from mobile hydraulics to all kinds of vehicles and linear drives and stuff. And within Bosch Rexroth, there was a strategic decision to combine all the industrial robots under this brand. And there's now two things. So the Bosch Rexroth company itself, they kind of do systems. So for example, they have an AGV called the Active Shuttle. That's, oops, sorry about that. That's one system for a specific use case. It's for like automation in production. It can transport those little blue boxes that you see in many factories worldwide. There's the APES robot, which is like a mobile robot arm with a synthetic skin on it that can detect human presence without touching. And then there's the home of robotics, and we have a little different approach. We focus on doing components. So that's not projects, but components, and that's more like the traditional Bosch DNA. So we do generic components that can be sold separately and scaled separately. So these components are not like complete robots, but customers of ours maybe need a solution for a specific problem, maybe want to build a robot, but be quick about it. So they can choose components from us, integrate them within their system, and then just speed up the development, or maybe solve problems which are not like defining their use case, like the localization, for example. So yeah, that's the components, and that's what we do in the home of robotics at Bosch Rexroth. I will talk a little about one specific component today, which we call the locator. That's for indoor localization, but there's many more in the pipeline. Yeah, so where does this component idea come from? This is kind of the situation we're facing on the AGV market. And what we discovered talking to many potential customers is that often a company builds a robot and outsources the complete automation. So there's companies in the market who do kind of the complete AGV automation in a black box that includes everything from sensors to the controllers to the motors and the whole automation software within one closed up box. And that's how it's been on the AGV market for quite a while. So as a customer or as someone who wants to build a robot, you had either the choice, you do develop everything from scratch up yourself, or you buy the complete automation within a black box. And what we're trying to do is break up this separation and sell modular components that can build up on each other, but also have an open API, so you're free to just use one or two of them maybe and build the rest of your robot around it. And that gives our customers the choice to develop key functionalities themselves, but still build up system know-how and have the maximum flexibility. So they have a speed increase and a cost reduction in just buying the component that they need for their system, but those functionalities that are critical for their use case, it can still build up themselves. That's what our system is designed for. And you can see there's a few components as an example in this picture. So we imagine the localization to be the very basis for every mobile robot. And then on top of that, we have the navigation, which does the path planning. Then there could be a hardware component like a robot control unit, maybe even a safety control unit, and many more components. We're flexible about this. We just started releasing the first component in 2019. So we do not have the full stack yet, but we are building up our portfolio fast. That's kind of what I mean about components. And now designing a component is a complex task. So the way we started out, we had a very basic SLAM algorithm that was developed at corporate research, and that had the kind of the level of developer code. And you find those in all different places. In many universities, you have great algorithmic choices, great algorithmic solutions, but they're kind of not finished yet to be actually a solution. And that's the starting point that we started out. And the goal was to have a sellable software component with maximum customer benefit. So it's not that much about the algorithm, but it's about the integration effort, which should be minimal. It should be flexible, platform independent in order to scale. It should be super easy to use. We don't want a bunch of experts trying to understand a component. It should be super simple. And then, of course, it needs to be reliable. It doesn't help anyone if the algorithm is nice and fancy in the lab, but then it fails every 5% in the real world. So it needs to be reliable, industry robustness, and a very high availability. So yeah, that's what we have in mind when we're designing a component. And you can already see there's much more to it than just the algorithmic solution. And just to give you an example about that, this is all the topics, or this is like some topics that we had to consider while turning an algorithm into a component. For example, there's the product development process, which we never considered when we just tune algorithms in the lab. But if you want to turn out an industrial component, you need to make sure that it's safe, that it functions in a deterministic way. You need to have a great API that's kind of static, that doesn't change with every release. And then there is data security. There's the thing of how you deliver the component, security penetration, and all this. So this is just a section of the topics that we had to deal with next to the algorithm. And the algorithm wasn't finished either, but that was for a long time not our main concern. We did add a few cool features, like for the localization and map update and kind of initial localization, but that's more like the bonus on top. The main work was to take an algorithm and turn it into an industrial component. Yes. And the way we do this is by heavily depending on data-driven development and simulation. So in our development framework, we have like terabytes of possible scenarios. We gathered those in 4 years of pilot prototype customer phase. We had many AGVs running in different factories collecting data. We had pilot customers who reported us critical cases. And from all those, we have the raw data in our system. And we do a KPI evaluation of every product change. So whenever there's an algorithmic change or some other change in the product, we have a nightly evaluation of this change to make sure that this not solves a local problem, but that this solves a general problem, and that we do not like, what do you call this in English? Like turn the screws on one side and solve maybe a little problem, but then screwing up many other problems on the other side. So we do evaluate all algorithm, all the scenarios we know. And on top of that, we build up a simulation using a Unity engine to create even more data. So if it comes to localization, I guess pre-recorded data, that's fine. If it comes to navigation, you kind of need a feedback loop system because the data changes depending on what your vehicle does. So that's what we have the simulation for. And we use this for our development data, but also for service and support, for example, where we can analyze customer problems in simulation and kind of see how the system reacts and what might be the underlying cause behind trouble that the customer might have. So yeah, this is like the main focus that we put our testing and our evaluation on this data-driven approach. So to be a little more specific, I brought to you the component that I already mentioned, which we call the locator. And this is a component for the localization and mapping of mobile robots. And I might say it's indoor localization and mapping. It does work outdoor too, but just to differentiate it a little from maybe a precise GPS sensor or something. So I said it's a modular component, so we ship it as software only because the two main pillars we focus on are flexibility and usability, because we found out it's not the algorithmic solution, but this is what the customer needs. And what I mean by flexibility is, for example, that we do not need any additional artificial infrastructure, but we use the laser sensor as our main sensor. And we just use the existing infrastructure to build our map and to localize on it. We can even use safety laser scanners that are already present on an AGV, so our customer doesn't have to add any specific hardware for a solution, but he can just install a software and use for localization. Like I said, we're hardware independent, so we ship our software in form of Docker containers that basically run on any controller that's powerful enough. I always say we need a little more than a Raspberry Pi to have a robust localization. But being hardware independent brings our customers a big benefit of choosing their own hardware, choosing their own sensor. Basically, we just need laser data and a computer that we run on, and that's it. And also we're vehicle independent. So what we do is we locate the sensor. What kind of use case you do, what kind of vehicle you have is not really something that concerns the software. Then the second pillar we focus on is the usability. And the usability is often a little neglected. I'm not sure if you've seen standard industrial machines before. They have like a gray touchscreen and a 200 pages manual that you completely need to work through. Maybe you even need an extra class to understand it in order to operate the machine. And we want to be the opposite. We want to be as easy as maybe a smartphone app. And so the main pillars for the usability are easy integration. That's why we chose Docker containers, and easy commissioning on site. So like I said earlier, we don't want a team of experts knowing everything about localization parameter tuning on site, but we want that everyone can build a map, that everyone can use our system. And of course, usability also includes reliable localization, and in our case, map update. That way, our customers don't need to worry about anything regarding the localization. And what that looks like, can you see here? So this is the video that I will play in a second. And this is the site that you can see on the left. And on this specific use case, you have like 2, 4, 7 different buildings. They're all connected. I think they're like 300 meters deep, 500 meters wide. That's about the dimension. You can see the trucks here on the lower left, and also the train tracks. And in this case, our software doesn't run on a robot, but on a manual driven forklift. And what you see here is the mapping drive. That's the main algorithmic feature we're very proud of. We call it one-click mapping. And the idea is that the mapping just is fully automized. So nobody needs to do any pre-settings. Nobody needs to do any map tuning. But all you need to do is start the recording on the vehicle, and then just cover the area that you want to operate in. And this is what the mapping looks like. So here in red, you can see the current scan, the current laser scan of the sensor. And then in white, you can see how the map builds up in the background. And this now is just a driver. It's just a standard fork truck driver covering the whole site. And he's probably going like 25 kilometers an hour. And there's nothing he needs to worry about to build the map. He just needs to cover the site such that we can build the map out of it. And this is the key benefit from this localization component. And that's what we're aiming for all our components, that we solve the problem for the customer, and that we not just deliver an algorithm, but a solution for the localization problem. Yeah, so this goes on for a while. And what you can see here, we just have the laser sensors, so there's no further integration needed. In the case of the fork truck, we don't have wheel odometry, which we could integrate if you use a particular short-range laser scanner, or if you have some free spaces that you want to cross. We can integrate wheel odometry, but the laser scanner is our main sensor, and it's automized in a way that the map building process is done on the fly, and there is nothing else you need to do. So there's no manual cleanup. There's no annotation of different static or dynamic objects needed, but it's all done automatically. And in this factory, so this is a wood factory, and so this is all block storage and dynamic. And I will talk about map update a little later. So we don't even know whether this is static walls or dynamic objects, but that's fine for the algorithm because it keeps it up to date with the map update. Yeah, I'm gonna fast forward here a little as soon as I can find my mouse pointer. There's a cool loop closure coming up that you can see in a second. Maybe not. Yes, here you go. You can see how the laser odometry had maybe little errors. You can see how the walls do not perfectly fit on top of each other. But as soon as we come back inside and get that loop closure, our algorithm corrects that automatically in order to get a more aligned map. Yes, and this is basically the locator product. This is what people and customers can buy out of the box since August 2019, I think. And it's already used on many different sites and many different robots. That active shuttle robot from Bosch Rexroth that I was showing earlier uses it too. And this is like this is what we imagine a finished component to look like. So like I said, I'm only scratching on the top of this. We have a graphical user interface built in Unity and all kinds of extras to this, but this is the algorithmic part of it. And the next little extra is here, the map update. So like I said, it could be dynamic environment too. This is a very old video, but it kind of shows the functionality very nice. It's a time lapse over the map of a warehouse, and you can just see how this changes day by day. That the rack storage area, that on the laser plane, sometimes you have wares in the rack, sometimes not. Down here, you kind of have a small commissioning area. I think the shipping is up here. And you can see how our localization keeps the map up to date. And these updates are shared among the whole fleet. So we need one vehicle observing an update, but every vehicle running our localization contributes to the current map and keeps it up to date. Yeah, so this is our localization component. That's the first component we went to market with. I guess the next components will be navigation and maybe a traffic management system or something. There's many new components coming from our side. And of course, we're always looking for new talents working with us on these new components. So if you're interested in this, just drop me an email afterwards. And as a future outlook, and maybe the way we use ROS is mainly in development so far. So we have a whole ROS tool chain.
Sorry to interrupt you. I
yes.
run out of the time.
Okay, then just one more minute. This is the last slide. Just to finish through. I'm just saying, having it in development so far, it's not very welcome for many industrial partners, but we see a strong need for standardization and norming on the robotics market. So I guess for future modularity and flexibility, I can see ROS2 playing a bigger role. And yes, time's up. So if you have any question, drop me an email, save them up for the later question and answer session. And thanks for listening.
Thank you, Timo. It's really exciting presentation.
Yeah, sorry when I was a little fast. I hope you got through with it.
Yeah, sorry.
That's all right. I'm excited for future talks. So thanks again, and talk to you later in the question and answer session.
Yeah, if we have still more time, we can discuss more in this panel discussion.
Okay. Sounds good. Thank you.
Let's go to the second speaker. Next one will be the Theo Rickert. He is working at Suit. Suit is a robotic and cognition startup in Munich. They specialize in the industrial processing of non-solid materials like textiles. So, microphone is yours, Theo.
Hello from my side, everyone. My name is Till, and I'm one of the co-founders of Suits. We develop intelligent cognition software for industrial robots, and we call it our robotic brain in a box. And with that, we specialize in industrial processes where non-solid or easily deformable materials have to be processed. For example, textiles or foils. And our vision is it to fully automate the production of clothes. But first, let me try to explain to you why this is so difficult to do. The main reason behind this are the complex material characteristics of those easily deformable materials. A textile behaves unpredictably and it changes its shape as soon as you touch it. And this requires enhanced handling abilities, which we as humans provide by default. Examples for this would be cognitive intelligence, sophisticated vision, process knowledge on how to deal with textiles, and mechanical sensitivity. And as a consequence of that, we have a lack of adequate automation solutions with processes that involve the handling of textiles of any kind. We combine unique process know-how on how to manipulate textiles with state-of-the-art computer vision and robotics approaches to create an unprecedented solution to that problem. We put all that together to what we call our robotic brain in a box, which equips industrial robots with a human-like understanding of those materials. And consequently, the range of possible automation applications is expanded drastically. Why? I want to talk about why the time is now. Why is this now so relevant? So you guys might know the big trends that we see that are very relevant for us, like robotic hardware is getting cheaper and cheaper, and this allows us to build automation systems at competitive prices. And in terms of computer vision, what is really important is that the processing power, the computational power that you can buy for the same price increases year by year. And this is very important if you want to train, but also if you want to deploy machine learning models for computer vision on edge later on. Also, the current pandemic has shown some crucial weaknesses of our global supply chains, and the world is demanding for more resilient supply chains. You can do this by relocating industries back to their markets, close to the markets. But if you want to do this in Europe, for example, you need automation technology to achieve competitive prices. And in the end, this will also then shorten transportation routes and reduce CO2 emissions, bringing us closer to a sustainable planet. All right, let's dive a little bit into the technology. I want to speak about the underlying computer vision that we use and how we develop our computer vision. So we use machine learning models for our computer vision, and with machine learning models, you always have the same bottleneck. That being, you need a huge amount of data to train those models. To solve that problem and to circumvent that bottleneck, we use FEM computer simulations, which were originally used to predict the mechanical properties of, for example, fiber reinforced plastics. And we took those FEM simulations and adapted them to simulate, let's call it non-technical or everyday textiles. Like on this slide, you see a towel, it could be a bed sheet, it could be a shirt, everything that's flexible. And with that, sorry for that, with that, we create a digital twin of the textile and apply photorealistic rendering later on. And the clue about creating these synthetic images is that you can have them labeled automatically. So what do I mean by labeled? For example, if you see the three towels at the center of the slide, in this case, we want to extract some features with our computer vision. And in the case of a towel, this would be, for example, the seams. So now if you want to train a machine learning model to extract those seams, you would have to label or to annotate those seams manually. And if you use synthetic data, simulated data, you already know where those seams are, and you can do the labeling fully automated. And compared to manual labeling, we save over 5 minutes per image. And if you calculate that for tens of thousands of images, we save days, sometimes even years of labeling effort. And this development pipeline allows us to quickly adapt our computer vision to different materials, different applications, different processes, and it gives us a huge advantage in terms of speed. Now that you can imagine a little bit better what I've been speaking about with these simulations, I brought a video to you. So what you see here is the simulation of a towel, which is falling down from a specific height onto a flat surface. And this is a video we created only for showing purposes in our computer vision pipeline. We would only then use, let's say, the last state of the towel, which you can see here, create a synthetic image out of it, have it labeled automatically, and train our computer vision with tens of thousands of those images. Now, this was a little bit about our computer vision technology. Now, I want to talk about where does this come into application. So one of our first use cases can be found in industrial laundries. Industrial laundries, you might not know that, but they're highly automated companies, but there are a few steps which still involve human labor. One of them is, you can see on the right in the picture, the clean textiles have to be separated out of a bin, then flattened out and placed into, for example, a folding machine or an ironing machine. And this task is more complex than you might think, and humans are still doing it. In industrial laundries, you have poor working conditions because of the high temperature, the high humidity, and the quality of the work suffers from the monotony. It's very repetitive. People do this from morning to evening, the same movement again and again. And this is why laundries cannot find enough workers to meet their demand. We created a system which fully automates the feeding of, for example, towels to folding machines, and we called it the Suits Velum system. And this system also gives our customers the opportunity to scale their production according to the demand, which is a big problem for them. And overall, 2.5 billion euros of labor costs could be automated with that system. I brought you a little video here. This is nearly 2 years old. It's the first experimental setup that we created to show a proof of concept. So what you see here is a towel lying in an undefined state, crumpled on the table, and then our computer vision extracts a seam of the towel and evaluates whether that seam can be gripped by those two robots. If it finds the seam, it calculates the coordinates for the robots. The robots then grip the seam simultaneously at the towel, and they slide it open just like a human would do. So we took the human approach and remodeled it with robotics here. And what you saw here is basically what workers are doing 8 hours every day in industrial laundries. Like I said, this is an experimental setup, or was an experimental setup, to give you a little idea where we are now. I brought you a picture of our current system. So to the left, you can see the intake conveyor of an industrial folding machine. This is a standard machine in every laundry. And we built our system in front of that, which you can see within the yellow-black safety fences. It is now separated into 2 units. And in the first unit, I have a video for you here. The first unit is a separation unit. So like you saw on the picture of the industrial laundry, the towels are delivered in huge piles on a conveyor belt or in a bin, and they need to be separated one after each other. And here we use our same computer vision. We extract seams of the towel, and we assess where can we grip something so that we in the end receive one single towel. And the complete process in the end is implemented with off-the-shelf hardware components, a universal robot in this case, a normal gripper, and only the gripping fingers we designed ourselves. And in this case, they are 3D printed. And after this separation step, we have a second component of the system where the towel in this case is flattened out and placed onto the folding machine. And unfortunately, I cannot show you a video of this here because of IP rights. I reckon there are a couple of people listening who want to know how we implemented this system on a deeper level. So I'm gonna talk a little bit about that. We have mainly 2 computational components. You can see in the center of the slide, the GPU accelerated IPC. We need the GPU to run our computer vision because the computation is very heavy and we need a GPU. And this IPC also controls both robots. On the bottom of the slide, you see a real-time enabled IPC, or a PLC, if you want to say so. It controls classical automation components like grippers, servos, sensors, everything that is not directly related to the robotics part. And it also hosts the human-machine interface for the end user, which is just a simple GUI with start, stop, error messages, system safety, very easy to use. If we go down a little deeper, on the left side, we again have the GPU IPC. It hosts 2 components. The first component being the computer vision. The computer vision we implemented in Python using PyTorch and OpenCV. So all of it is self-developed, and it sends grasping coordinates and a manipulation strategy to the robotics component. By a manipulation strategy, I mean, for example, the computer vision identifies, is this a towel we can manipulate or not? And if not, the towel needs to be removed, for example. This is manipulation strategy. The robotics component then processes these information, and the robotics component is set up with Python, CPP, using ROS-I, move it, and the robotic state machine is implemented via the ROVCon package of DLR. And this robotics component is communicating with the integral system controller, which is hosted on the real-time PLC via a customized Ethernet TCP/IP communication. And we're exchanging important system data, like which component is where, to avoid collisions and that kind of stuff, and to orchestrate the overall system. And then there's a fourth component I marked in red. Why did I mark it in red? It's the safety controller. So the safety controller is essential for the industrial certification of the system. And the safety controller is hosted on the real-time PLC, because this device is already certified for it. And it operates on a complete separate level from all other components and completely separated from ROS. This means no matter what ROS or something else tries to do with the robots or other components, if the safety controller puts the system into an unsafe state, nothing can move anymore. The system controller has priority over all components, and this allows us to get an industrial certification for our product. All right, so I talked about our first use case. I want to expand this a little bit. So other use cases which are relevant for us is the order and return picking in e-commerce, the manufacturing of car seat covers, the production of fashion and homeware, but also harvesting and food related processes. Basically, all processes which involve easily deformable or non-solid materials are interesting for us, and we can automate those for our customers. My two co-founders, Alex, Tim, and myself, we've known each other for over 8 years now, and we founded the company nearly 2 years ago. As of today, we have grown up to 16 people, and we will grow further. There's no end to it. Currently, we are shipping first Velum systems to customers, and we are raising our seed financing round. So please feel free to ask any questions later on in the Q&A session, or contact me after this event if you want to learn more about suits, what we do and how we do it. Make sure to follow us on LinkedIn to always stay up to date. And yes, we appreciate your support to automate the world. Thank you.
Thank you, Theo. It's really impressive presentation. And yeah, let's go for the last speaker.
Thank you.
Yes, the last speaker is Dario Ro. He worked at the robotic division at PILT, which also called the Competence Central Robotics. And the goal for them is to bring ROS to the industrial and bridge the gap from innovation to production-ready systems.
Thank you for the introduction, Rushao. And so, like you said, our goals at PILS has been to bring ROS to the industry. And of course, since we are PILS, it is to do so in a safe and certified way. So for those of you who don't know us, we are PILS and we work on safety automation. And one interesting thing is that if you have seen the logo for the ROS Industrial, the robot that appears in the logo, that is our robot. So among other things, we also make sensors and a variety of services for safety and assessment. So we asked ourselves, is ROS safe, or can we make ROS safe? And how ready really is ROS for us to implement it in a production machine, in a plant floor, working 24/7? So this is why we built a robot with first-class ROS support. And now we have built a full certified machine to find out if it's possible. And I have already spoiled the answer, but I will talk about this in this presentation. So the first thing we ask ourselves is, should we automate this process? So in this case, the process that we wanted to see if we could automate is a 2D inspection process. So of course, in the industry, we always ask ourselves if it's necessary or if it's better at all to automate this process. So let's take a look at the existing process before we build the machine. So this was the existing system. It's an array of static cameras posed to inspect, in this case, one of our famous safety relays. So in this case, we have an array of 4 cameras that take static pictures of the relay that you have to place manually in this picture. And as you can see, we can find a couple of problems here. So if we want to change the part to inspect a different product or even a different reference within the same product line, it's not possible for us to, for example, move or shift the position of these components. In addition, this means a higher cost because it means that we cannot buy more cameras, or we have to buy more cameras if we want to add more positions. And it also means that we have some dead zones in the product that we cannot see or inspect to access. So this is where our robot system comes in, and it's a much more flexible alternative for that. And it allows us to go even further and even improve a little bit on the costs and the ROI of the whole application. So first off, it gives us a much higher flexibility, not only in the part, the dimensions, and the type of thing that we are inspecting, but also in the tooling, in the software, and the whole process of building the machine. Because as you know, there is no 2 equal machines or 2 equal robotic applications. And so it's very important as well that the process of developing them is as seamless and as easy as possible. Then we, of course, we have a lot fewer dead zones, so we can access a much wider section of the product to inspect. We can have, again, a better return because we don't have to spend a lot of money on cameras, on materials. We can allocate those resources to other things or save it altogether. And lastly, this machine is fully CE marked and certified with its whole machine lifecycle and necessary documentation, and in addition to being made with ROS. So that's what's the interesting part about it. So talking about 2D inspection, this is a topic that can take us probably hours to talk about. But in short, our machine can perform a wide variety of inspections. So as you have seen, it's equipped with a Cognex 2D camera. And this camera performs the analysis itself on board. So it's equipped with a processor so it can perform some of these inspections. So just to give you an idea of the types of things that we can inspect, we can take a look at mechanical defects. So that means surface, scratches, dents, that sort of thing. Then we can look at presence and validation of assembly of certain components inside the part that we want to inspect, or identify it via codes, QR or barcodes inside the part. Then we can also inspect details for measurements, so gauges in this case for alignments. And we can manufacture, check for manufacturing and cosmetic defects of all sorts. So as you can have seen, it's very useful for the assembly and for assessing the quality of components in a variety of areas and in a variety of sectors, actually, which is what's interesting, that we can use the machine in a wide variety of sectors, and it's quite a flexible solution. So what did we do in our case? What we did, as I said, is inspecting relays. So more specifically, what we did was inspecting a bunch of parts inside the relay. So in this example, you can see that we were looking, for example, first at the barcode in the relay to identify the exact part and the serial number. Then we also were looking at the presence of this little bridge here for some connectors. Again, all these were parameters and they varied depending on the part. So that's also the interesting part of working with a system with ROS. And I will go into detail later about this. Then we also looked at the part designation. And this is where it gets quite tricky because I remember we were inspecting once a piece and I was running the robot and the application, and I saw that the inspection gave a wrong result. And I said, this is not lining up because I cannot see the difference. And then looking at the picture and zooming in, I could see there was a very small imprint of the ink in the image. So that gives an idea of the sense of this camera and the fact that it can be quite powerful, even if it's working again with ROS on the backend. Then we looked at a designation and the rotary switch, so the position of this rotary switch inside this wheel. So as you have seen, it's quite a lot of data that's related to each part, and that has to line up with what we are expecting of the inspection. Of course, we did not do this for just one relay. We actually did it for a total of 43 references. So these are just some of them. Some of them had up to 20 different inspections. So This meant a very high volume of data to both collect and to have stored so we can easily access once the operator tells us what we have to inspect. So again, with ROS, we could do this a lot more easily, as I will show you in the software architecture. And that probably saved us a lot of effort and work in the programming part. So let's take a look at the actual cell itself as a whole. So the software build looks like this. It's a standalone cell that you can use anywhere, again, in a floor plan. It has, of course, its main components, so our manipulator and its operating modules for control and visualization. Then we have our specific application components. So that means a modular tooling, the camera itself, tooling for the infit of the part itself. Then we have interaction devices with the operator. So that means an intuitive HMI and the barcode reader to identify, again, which parts they are inspecting. And as you have seen, this is only part of the machine in reality, because for it to be a standardized machine, we need safety components, and quite a few of them, as you have seen. So from safety curtains to, of course, mode selectors, stop buttons. So all these components are necessary and normatively required for an application of this kind. So as you have seen, the robotic system itself is only part of the application, and it's important to design everything in conjunction. So something you will not see in a picture is all the effort that went behind and the work that went behind the machine life cycle. So that means first designing with a safety designing concept. So it's important to start designing from scratch, considering the safety and how you're going to operate the machine and how you're going to validate it. Then it's about risk assessment, of course, in order to properly mark the machine. And finally, again, CE marking and all the documentation that's necessary, factory acceptance tests, and so on, which is not to be overlooked and is incredibly important in these sort of projects. So with all this in mind, what we want to see is that with ROS, can you actually take account of the machine life cycle as a whole? So what's going to happen with this machine 5 or 10 years from now? How am I going to provide support for it, and so on? So like some of our colleagues yesterday talked about with security, and I recommend watching those talks. Safety is also a continuous cycle. So it's not about just doing it once and leaving it as is. It is something that we need to consider the machine over time. So for example, how are we going to handle updates, or how are we going to even expand on it? And those are the sort of things that we wanted to really think about with this machine. So as you have seen, this is the high level sort of architecture in terms of components. This is the architecture in terms of hardware and connections. So this gives us an idea of how we have been able to certify this machine again and make it proper. So in this case, with manipulator, of course, we have our typical ROS control system. So thanks to our first-party native packages, we can control the robot directly with CanOpen with an industrial PC. And also we can connect it directly via network to the rest of peripheral devices that we need. But most importantly, as you have seen, the safety of the whole application is managed by our PSS 4000 safety controller. So thanks to this architecture, as you have seen, all of the hardwire connections, so both single and dual channel, are connected to our safety PLC. So that means that this safety PLC is made for this task already, and we don't need to work harder to make it compliant. So one of the caveats of ROS is that it's not handling safeties just yet. So to solve this and to be able to properly put the machine up to standard, we use our safety controller. And this architecture allows us to have more freedom in the ROS part on the one hand, and second, not worry about the safety for now inside ROS. So as far as software architecture, this is where it gets more interesting. So first, we have, of course, our very own PLC packages. So these PLC packages include support first party that we make ourselves. So these are first party packages that we have developed in conjunction with the hardware. So we include, of course, your typical packages for description, for move it config, so you can get up and running and programming the robot. In addition, we offer an API for programming the robot, which was quite nice to work with throughout the whole process. And then, of course, just as important is our hardware nodes and packages. So with these hardware support nodes, we can connect with the real robot. And this makes it quite seamless to work with a simulated robot and then translate it to the actual robot. This was quite useful, one, to run offline simulations and develop in parallel. And two, it removed a lot of friction in the stage of actually handling the safeties and the signals from the machine. So this is where we'll start our work. So using the Pilz Industrial Motion package, which, as you may know, is now being used by many robots, and I'm very happy to see that in the wild, which is the deterministic package for motion control with the robot. So this gives us the robustness of your typical PTP link commands that you're used to with industrial robots. Now you can have it within ROS. So what we did was we created our inspection packages, and the backbone of these packages was our own process manager, which was a state machine. So this could be a very long discussion because making your own state machine comes with its own set of nuances and considerations, but we opted for a state machine to make the process simple and somewhat single process, even though it actually needs a bit of concurrency here and there. But this kind of logic allows us to take into consideration things like safety, which usually are not considered in process flows for state machines or for example, behavior trees. Then we built our inspection commander to actually control the robot with the Python API. So this was a really nice part to work on because, again, a lot of the work and the heavy lifting is done right here with the industrial motion package. So then what was left is interfacing with the Modbus camera. In this case, the Connex camera was working via Modbus, and we wrote our own wrapper around it to interact with it. So this meant triggering the correct program and gathering the data, configuring the autofocus and the exposure of the camera, and so on to have the best possible result. Then we built our own sort of pipeline for us to develop our application more easily. So what we did was we set up a SQLite database for all our references and our inspections, which were more than 800 in total. So quite a lot of data if you consider, for example, discrete programming of traditional systems. And then we parsed it from a YAML file to have it readable and ready to redeploy and refresh every time, and for it to be easy to work on. So with all these, we built our own custom system with a jogging with the controller. And what this enabled was for one of our colleagues who was very proficient in vision to program the vision of the relays without the need for him to learn ROS altogether and to understand all the architecture. So this is one of the, again, benefits of ROS, even in a fully compliant machine. Then, of course, we interface with the barcode reader with a very simple C program that we wrote. And we interface with the PSF4000 with the well-known PyModbus package for Python. Then lastly, we have our HMI, which we will talk about as well. And we interfaced with it via a great, again, community package of OPC UA. So again, this software modularity allowed us to do lots of things, build our own development environment, and make our own process easier and faster. So this was quite interesting, again, not only from the viewpoint of the final result, but also from the viewpoint of working on the machine, which is also important if you want to reduce the cycle and the iteration time, because of the whole process, as you know, can be quite repetitive, especially with 800 different inspections to perform. So we built inspection controller tools, like I said, a custom state machine, and our driver for the Cognex camera. So even though we are not planning to open source these components, they are assets that we have now and that we can take advantage for future projects as well. So we've already talked about, again, about the HMI that we have and the case of this HMI. The idea is to have ROS as a backend technology. That way it can have a front end that is intuitive to the operator, and the operator doesn't need, of course, to learn ROS. And we can have a lot of information for it to be easy to use. So the idea, again, was to have a very user-friendly HMI with a view of the progress of the inspection and what's going on in the machine, and even have some historical data for how other inspections have performed. So this allowed us to use ROS, like I said, as a backend technology of sorts, and see how it could help us make the machine faster and also intuitive, which is something that ROS itself isn't quite yet, especially from a development standpoint. So as a closer, I would also like to show you the machine in action. So let's see, this is one of the longer inspections. So that's why it takes about 1.5 minutes. And you can see, you can see the whole process of how the machine behaves in a full cycle. Let me see. Can I get it to play? So allow me, let me zoom out a little bit. Okay, let's see it like that. So as you can see, the operator, which is our engineer, Javi, here is putting the barcode to identify the part. The machine is informing him with animations of what he has to do in the panel. And then he is performing the loading of the part. Then he needs to press start, and the machine tells him what he has to do at every stage. And now we start the inspection. So as you have seen, in this case, it was quite interesting to work with because thanks to our planner, it's quite predictable where the robot will go and how it will behave. Also, and even though you will not be able to see it here, you can have an interruptible machine. So if you, for example, cross the light barrier, you don't need to restart the whole cycle because the machine already knows where it was and how the robot was located before. So as you have seen, I can also check the status of the inspection, even though it's not very clearly visible on the screen. Sorry about that. And you can monitor how it's progressing when the inspection is going through. So in this case, like I said, it's one of the larger inspections, so about 20 inspection points in total. And in this case, it's inspecting one of the relays fields. So again, the operator doesn't know or doesn't need to know that this is made in ROS. This is a front-end solution. In this case, it's using the PathVisu software, which is made by us, by Pils. And so it was nicely integrated with ROS, with all the aforementioned architecture that we showed you before. So I think I'm going to cut it short right now. And you can see the final result. It detected an error. And so there was one part of the part that was not correct. So let's get back to the presentation. So that is our vision at Pils of the future of automation. It's a future of different hardware architectures, different hardware styles, and a wide variety of components that work together in a modular way. In addition to the manipulator, we also make packages, first-class packages for our scanner, our laser scanner, so you can output laser scan data and actually use it inside your ROS navigation stack. So that's about it from my side. Thank you very much to everyone for the presentation. If you have any questions, please reach out to our ROS specific address, or you can visit us at our booth here in the ROS Industrial Conference. Thank you very much again to everyone, and I will hand it back to Rochelle now.
Thank you. Thank you. It's really nice presentation. So now we move to panel discussion. I think everyone can switch on your camera. Okay, yeah. So let's start from Timo. Okay, I thought there's quite a lot of interesting questions on the live discussion. Yeah, the first question for you is how do the customer deploy the Docker image or update in the production?
Thank you. So that really depends actually on the customer. So since we're just one component of the whole customer system, many customers build up their own solution. Some put up a Docker registry and the robots actually pull the image at the commissioning on site. Others just import the image during manufacturing. So it really depends. If it's a large scale machine manufacturer, the image is usually loaded onto the computer during production. But if it's more like a project-based customer, it's usually with a registry or even with a USB stick, like during the commissioning. It depends on the scale of the customer, I guess.
Yeah, thank you for your answer. But then that means the customer need to have this Docker-based production.
Yes. So that's our only interface to the customer system, right? We thought about many ways how we could decouple a software component from the whole customer system, and Docker seems to be a good way since due to that Docker host, Docker container architecture, we have very little dependencies to the customer system. So he could run even a different operating system and our container will run isolated or part of software and he will have the API to communicate. Yeah, so the Docker is one dependency that we have.
Yeah, good. Thank you. And I think there's another question for you. It's, can you tell us more about how you use ROS in the locator? Is it only used internally or it also has an interface to the other components?
Yeah, I noticed I was a little short on that topic. So we use it completely in our developing and testing tool chain. So all the code development, all the testing, all the validation is done with a complete ROS tool chain, the RVIS visualization and all that. But actually in the product that we deliver to our customers, there is no ROS. Because when we went to market, there's many customers who said that they don't want ROS in an industrial component. So we put up our own proprietary framework, and in the shipment to the customer, we don't have ROS for now. We do have a ROS node as kind of a wrapper. So if a customer wants to use our product with ROS, he can implement or install this ROS node and connect to our interface. But we only use it here in our office because with ROS-I, there was many customers who didn't want it in industrial products. But we hope that changes with ROS-II. It's actually kind of a not so nice workaround, and we would love to ship the product like the framework we have it here. But that's a workaround we had to take to go to market, actually.
Okay, thank you, Timo.
Yes, you're welcome.
Yeah, okay. Here I also have several questions for Teal. Yeah, the first question for you is, okay, let's start from easy one. What type of camera do you using for the machine version?
So we've tried a lot of 3D sensors ranging up to 15 to 20,000 euros for our application, but in the end you need to try to get the costs down. And currently we use a standard 5 megapixel industrial RGB camera. It's from IDS if someone's interested. And we use a LiDAR sensor, which we found that it, for the price, it costs like 300 euros and the results are very impressive.
Okay, yeah, thank you. Then the second question for you is, how is the intelligence of the movement implemented? Like, for example, the video you showed, the first video. How do you handle the different size of the tower, and how do you handle the specific movement for the folding? Yeah.
Mm-hmm. Yeah, that's a good question because it's one of the key points. So this whole process of sliding alongside the seam of a towel is quite complicated. If you as a human do it, you control the force several times per second. And in order to on the one hand, not lose the towel, but also not to damage it. We do the same. So you might have recognized that the grippers are pretty massive for such a light object like a towel. But with those grippers, we can control the force down to 0.1 newtons several times per second, and we do it like a human. And then for the width of the towel, we use very, very easy optical sensors to detect whether we've reached a corner of the towel and stop the movement and increase the gripping force so that we don't lose the towel.
Okay, so basically the force is you need to set up the manually, or it's automatically learn how much force you need to apply to the gripper.
Mm-hmm. So this is done. We've created a calibration procedure for that, which looks like you put in a towel and we apply some forces to the towel, and in the end it generates an output which is a good force for this kind of towel. We do this with many towels, and by now we're able to handle lots of different towels.
Okay, thank you. Yeah, and another question for you is which type of the commands do you send from the GPU IPC to the PLC IPC, and how do you connect them together?
Mm-hmm. So currently we're using a Beckhoff IPC. So Beckhoff is building on EtherCAT. Let's say it's not that easy to connect via EtherCAT to a Linux system. So what we did is we implemented a socket communication, TCP/IP, with a custom protocol. Basically, we're sending back and forth in a cyclic manner status words with different system informations. Yeah.
Okay, yeah, thank you. Okay, so I do have a question for the Dario. I think there's some delay. The question maybe they didn't show off, or they still watching your presentation. So I saw you have quite a lot of components for the Pilz robot. Is it all the open source, or it's also possible to implement to the other robot? Because I think the few of them is quite impressive and really useful for other robots too.
Yeah, so there's of course a part of it that is very specific to our robot, but then there is a very interesting part, which is the command planner for the trajectory generation, which is an industrial trajectory generation, like we say it. So it's deterministic. And this is the main component that we are integrating into the main MoveIt branch. So it will be available for lots of robots going forward. And of course, you can always take a look at our code and see how it's implemented in the hardware architecture and see if you can build an equivalent in your robot.
Okay, thank you. Yeah, we also have some question in the post. So, we also get some feedback from them. For example, so the first question is, do you think the ROS is ready for replace the traditional robot systems? And we have 53% people say yes, and 37% people think no. Okay, basically half people think. Yeah, so how do you think can ROS replace the traditional robot system? Yeah.
Well, I'm not sure. I think we maybe need to separate a little between like those robotics arms as traditional systems and mobile platforms. And for mobile platforms, I don't really see a traditional system. And I think that's where ROS is really strong, because there's not a defined way of what they look like or what the kinematics are. And this is like one of the strengths of ROS, to adapt to it and to be even adaptable. So I think for mobile robotics, ROS is a very strong player in the market, and there's nothing to be replaced also.
Yeah. And Dario, do you want to say something?
Yeah, so I think it's similar to Timo. In the end, it depends a lot on the hardware that you're using. So first, I think it's very important to have first-class support for packages, or at least a very robust set of packages. And then from there, I think you are good to go. But for ROS, in my opinion, you can right now build a very good system. And like Timo said, for mobile robotics, there is almost no choice.
If I may add to the industrial part of it. So it also heavily depends on the robot you're using. So there are different robot manufacturers which are directly involved in the development of ROS Industrial, like the ROS Industrial drivers, and other manufacturers are not involved and third parties are doing it. And this is a big difference. So if the driver itself has already, let's say, bugs, then it is clearly not fit for industrial use. If the driver is good, most of the stuff that comes later on, you can manage.
Yeah. I think it also leads us to the first question. So what is the biggest barrier of the entry to create the certified application for you? So I think, yeah, most people think about it's the quality of the results. I think it's also we think about how stable, how robust the driver for the robot it is. Yeah, so how do you think about that? So what is the biggest barrier for you of the entry create certificate application for you? So how do you think about that?
I guess from a salesperson view, it's more that customers are being skeptic about it. So it's not really a technical barrier from our development side. It's just that some customers are kind of conservative of what software they want to use in their products, and that's more what's keeping us back. I guess from a technical side, it's very simple and easy. We could start right away. So it's maybe more like an image or like a security topics, not as much a technical framework topic on our side.
Yeah, so you think the software actually it's really just depends on the user. Are you ready to use it or?
Yes.
Yeah.
So if I may add to that, again in the industrial focus, it also depends on your application. If you have an autonomous vehicle, which possibly can even kill people or injure them, this is something different compared to a robotic cell, which is protected with safety technology, like Dario was showing. And in this case, to get a certification, if you, like also Dario was showing, if you separate the safety controller from the ROS part itself, then you can get a certification for that system.
Yeah, thank you, Theo. And Dario, do you want to say something about that?
Yeah, so I think that Timo and Till both have said it. The user perception and the perception in customers right now is the biggest barrier. So by building this application that we showed today, I think we have to show them that it is actually possible to build compliant applications.
Yeah, okay. Yeah, we almost are run out of time. And yeah, at the end, I want to say thank you for your presentation today. It's really impressive and it's also give us a lot of idea. And I think the discussion also quite helpful for us. And yeah, enjoy the rest of the conference.